So if you have any questions, you can ask. So I'm just going to assume that you have no questions. I mean, to me, the answers are kind of obvious.
I wasn't entirely sure what to do for the last question because I had no understanding of what the date even was, because that's not in a table we've used before.
Yes, I mean, you don't really need to, even if this was if it had been A, B goes to C. So what it means is that you can only have one value for C. So if you have A1, B1, it can only be, C. You can never have A1, B1 going to another value, say C dash. You can never have that. So if you look on the options that were given, the only option that states, I mean, this particular thing that you can only have one particular value for given A1, B1, there can only be one C. You cannot have a C dash. B is the only option. So, so you don't really have to know what anything really means, but as long as you understand the meaning of functional dependency. So if you look in the first one, it says an employee cannot work on multiple projects on the same date. That is not what this means. You could have, so this is perfectly fine to have A1, I mean SS number. So you could have SSN, same SSN, and he could work on P1 on the same date, and he could work on P2. That's perfectly legal. So the first one is that's what it says. The second one, it really just says this, that an employee cannot work on the same project on different dates. Then an employee must work on all projects on the same date. No, that does not mean at all from that functional dependency. And then none of the above information. So you don't really have to know the meanings of any of those things as long as you understand the meaning of functional dependency.
Right, I think A, B, and C would have been clearer to me because I said you couldn't infer it because like we don't know if that date is like the start date an employee started or the work date or anything else.
Yeah, but you have to look, I mean, you have to do it in context, right? Of what the question said this. So you have to work on context of, I mean, on what the question was stating. So here you had SS number, P number, and date, and so you have to find the best solution based on that. So the B part is the only one that does not, contradict that A, B goes to C. So none of the above is also not correct. So, I mean, if you can ask, I know that it may be you're still not convinced. So you could, stay on if you want after class today or during office hours, and I can come back and explain this, try to explain it better. Yeah, but always, I mean, you have to answer these questions in context of what's given to you, the info that's given to you. Is there anything else? I've also put up, there is no assignment due this Monday. And so this assignment is a bit different from previous assignments in the sense that, I haven't done the PHP, the web-based access in class, because I mean, really there is no time, and, doing PHP is, I think it's covered in some other classes, but I put up labs that really go over the stuff. And I also have put up PowerPoint slides, a little bit outdated because that PHP interface keeps changing. And it's a real pain updating everything. But the labs are all based on the latest information. And even in the assignment, you just have to fill in certain parts. I've done the skeleton and all, and you have to fill in certain parts. So, I mean, it's, if you already know PHP, it's going to be a very breeze. You can do it very quickly. If you don't, it might take you a little bit of time. So I've kind of given you 2 weeks to do this assignment. Okay, so then let me continue with the third normal form. So, so in the class, I gave the algorithm last time. So, I mean, I think that someone had asked me a question about this R1, R1 dash and R2 dash. So I think the best way I figured out is to put it like this. I think this is better. And as long as you understand that when you divide R dash into R1 dash and R2 dash, the common A bar has to be common in both. The key of the R1 dash has to be brought down to R2 dash, as long as because there has to be an attribute that links the two tables. So let me show. So we were doing this particular example in class. So you have this relation R, and it's got two functional dependencies. And this table is not in third normal form because of the second functional dependency. D number determines manager and D name, but D number is not a key, and manager and D name are not prime attributes. So this table is not in normal form. So therefore, you go to this algorithm. So first you have to compute the keys. So the key for this large table is SN, SSN. And that comes directly from FD1. You don't have to go any further than that, because FD1 shows that SSN determines all the other attributes in the table. So after that, you have to repeat until all relations are in third normal form. So pick any R dash. So in our case, R dash is the stable R with functional dependency A going to B that violates third normal form. So we're going to pick up the second functional dependency, FD2. And then we divide R dash into two tables, R1 dash, and R1 dash is, you pick up this functional dependency. So D number going to manager and D name. And then R2 dash is, so you have to bring D number down, and then it's all the other attributes that were not in the other table. So we have SSN and name. So now we have two tables, R1 dash and R2 dash. So now we have to look at table R1 dash and see, is R1 dash in third normal form? So R1 dash has got only one functional dependency, that's D number going to manager and D name, and D number is the key, right? So therefore R1 dash is in third normal form. Then you look at R2 dash, and R2 dash only has one functional dependency. SSN determines name and D number. So again, R2 and SSN is the key for R2 dash. So R1 dash is in third normal form, and R2 dash also is in third normal form. So now from that one table, we have two tables, R1 dash and R2 dash. And so they are both in normal form. And if you can get the original table R by joining R1 dash and R2 dash. And since R1 dash and R2 dash are in third normal form. So do you understand this example? So now at this point, you can stop. All you want is third normal form decomposition. So this is in third normal form, so you can stop now, because R1 dash and R2 dash cannot be decomposed further. I mean, it is in third normal form. Okay, so let's do a few more examples. So let's look at this next example. Okay, so we have this table R, which is D number. So I'm going to kind of use this example since you're sort of familiar with it. And then we are given three functional dependencies. We are given FD1, which says D number determines D name, school, and building, which means that D number is a key because it determines all the other attributes. You're also given that D name determines D number, school, and building. So again, since D name determines everything else, so D name is also a key. So that you have two candidate keys, D number and D name. And then you have this third functional dependency, building determines school. Okay, so now we have building determines school. So we have three functional dependencies. And so if you look at this, you know that it's not in third normal form. So let me just see, the keys are D number and D name. They both are keys for this relationship. And R is not in third normal form because you have FT3, which is building determines school. So we have and building is not key. And school is non-prime. So it's not in third normal form. And so we have to divide this into third normal form. So again, the way you start is you look at FD3, the one that is violating the third normal form, and you start from that relation. So you divide the table. So you divide in a table, say R1, which is you pick the functional dependency that's violating. So that's building and school. And the key here is building, because building determines school. And then you have R2, which is all the other attributes other than the fact that you bring down building. So we have D number, D name, building. And out here, you have two different keys. So I cannot underline because there are two keys here. So we have D number is a key, and so is D name a key. So we have two keys. So out here, we both R1 and R2, they do not violate third normal. I mean, there are no constraints that violate third normal form. So both R1 and R2 are in 3NF. So and R would be the join of R1 and R2. Okay, so that's how you divide this particular table into third NF tables. Okay, so let's look at the next example, unless you have any question on this example that I just did.
In R2, are both DNO and DName a combined key, or are they separate potential keys?
They are both, they're candidate keys, because D number determines all the other attributes. So it's a key.
Right, okay.
And D name determines all the other attributes in the table. So it's a key. So out here, the same thing. So D number, so if you, D number will determine D name and building, and so would, just one, I'm running out of, okay. Let me just move this down a bit. I don't have space here. Okay, and so would D name determines. So they both are keys. So that's why I didn't underline, because if I underline, then it will look like D name, D number, D name together determine building. So when you have candidate keys, just write it outside like I did out here. Okay, so we have, so let's look at this next example. We have R, which is, again, I'm just going to stay with this example for a while. D number, school, dname, building. And you have the following functional dependencies. You have FD1 that says D number and school, determine D name and building. So which means that D number and school is the key. And then you have another FD2 we have is that school determines building. Okay, so we have so the question again is R in third normal form? So so we know that the key out here is D number and school together, because D number and school determine all the other attributes. So the question is this in third normal form? So let's look at FD2 because that's the one you have to look at. FD2, FD1 is perfectly fine. You have, that's how we picked up. So we have the second functional dependency that is school determines building. And that's the one that's going to create the problem, because school is, yes, it's a prime attribute, but it's not a key. I mean, so it's not a key. It's a prime attribute, but it's not, school by itself is not a key. It's just part of a key. And building is not prime. So therefore, R is not in third normal form. So we have to divide it into third normal form. So again, you pick up FD2s. So you have R1, which violates, and then you say school, building. And in this case, school is the key. And then you have R2, where you bring down, you have to bring down school. So and in this case, D number and school together are the functional dependencies. So we have, here we have this, and here we have these two determine this. So now R1 and R2, they are in third normal form. So so we have and then R, the way we divided it, it will be equal to the join of R1 and R2. Okay, so do you get this so far? Are you with me? Okay, I'll take silence to mean yes. Okay, so now let's look at this next one. And again, we'll take the same example. We have R, D number, D name, school, building. And now we have FD1, which is D number and school, determine D name and building. So far it looks like the previous example, but let's look at FD2. Okay, but now what we have is, so in the previous, in FD2 out here, we have school determines building. So now I'm going to switch it around. I'm going to have building determines school. Okay, so that's the only way this one and the next, these two examples differ in their functional dependency too. So again, the question is R in 3NF? So let's look at this. So the first thing is, what is the key? So, so if you look at FD1, which says that D number and school, so D number, school, they determine all the other attributes. So D number school is a key, but D number school is not the only key out here, because you are also given this FD2 out here, which is building determines school. Okay, so so remember we did in the last class we had done you know, if A determines B and B determines C, then A determines C. So we had this, so I think this was in a previous lecture. I can't remember which lecture it was now. But we had this rule. So it was A transitive property, B determines C, will imply that A determines C. So if you go to FT2, it says that building determines school. Okay, so and then you have D number and school out here. So we have determines whatever D name and B building. So which means that D number and building will determine, you know, whatever we had out here. So therefore, this table has two different keys. So the first key was very direct, but the second key you have to apply that rule. So we have D number and building will also determine D name and you know, whatever school and building. So we have two different keys out here actually, not just one key. D number and school and D number and building. So did everyone understand this part? Okay, so now let's look at FT2. So FT1 is not a problem. So let's look at FT2. So we have building determines school. Okay, so now out here we have building determines school. So building is not a key, so that's not a problem. By itself, it's not a key. But D number and school, so D number school, so school is part of a key. So therefore, school is a prime attribute. Therefore, if you recall, third NF is that either the left-hand side has to be a key or the right-hand side should be a prime attribute. So therefore, you know, R is in third normal form. So neither FT1 or FT2 violate third normal form. So therefore, R is in third normal form. So you don't, if you, all you want to do is bring the table down to third normal form, you can leave it as the original table. So do you understand this example? Okay, so it's in third normal form, but the thing is, if you look at a table, so I'm going to bring up, put a small example table out here. So let's say, so this is the table R. I'm going to show a small example, D name, school, building. So that, okay, so we have, so let's say D number is 1, D name is CS, school is SEPS, and building is Kingsbury. Okay, so D number is 2, Earth Sciences, SEPS in Morsol. So Math Department, SEPS, Kingsbury. Then D number 1, Nutrition, Colsa, Thompson. I couldn't remember the name when nutrition is done. So, and let's say we have Earth Sciences again in Colsa. And let's say it's in. Okay, so I just wanted to, so if you look at this, so this table R, it follows this, it's a table, I developed for this particular example. And if you look at this table, and like I said, this table is in third normal form. So, it is, it doesn't have to be divided any further. It is in third normal form if that's all you want to bring it down. But so building determines school. So we have these dependencies. So we have Kingsbury should Morse is in SEPS. So whenever you have Kingsbury, you should always have SEPS on the in the school. And whenever we have Thompson, we should have Colsa. So so building is determining school. So if you look at this table, there is some redundancy in the table. So even though it's okay to leave it in third normal form, the table still has some redundancy. So that's the thing is. And remember, whenever you have redundancy, the problem is whenever you insert, you have to make sure that whenever you write Kingsbury for building, the school has to be SEPS. So you can have these insert, delete, and update anomalies. So then, for example, I remember years ago, I mean, this has to be when all of you were babies or something, the old Kingsbury building, none of you will remember, it was a horrible, horrible building, the whole old engineering school. When I joined this place, it used to look like a factory. So then they had to completely break down the old building and bring up the new building. So computer science, most of the departments in Kingsbury had to move out. Now, I forgot the name of the building that we moved into. I mean, initially they said it was only going to be a move for a year, but we ended up being in this other building for about 4 years, I would say. So this was years and years ago when it started, you were babies. And I guess when Kingsbury was finally built, you must have been by then in elementary school or something. So anyway, so that's what I meant, so the problem is that, you can have delete anomalies too, so suppose suddenly SEPS moved into some other building, we wouldn't know where Kingsbury used to have SEPS and stuff like that. So that's the point I was getting to anyway. So the whole idea is that there is all this redundancy in third normal form. So sometimes, even it might be a good idea to further divide your table so that you don't have this redundancy in there. It might be a good idea to, again, divide this table into another table that has building and school as a separate table rather than putting building and school in the same table. So that's where we get into the stronger normal form, which is the next one. From third normal form, the next higher normal form is Boyce-Codd normal form. So that's what the next one. And just aside, I do want to mention that there is also a first normal form and second normal form, which I'm not doing in class. Mainly because I think that at the very minimum, you should bring tables down to third normal form. You shouldn't leave it in less than that form. But in an assignments, I won't ask you maybe on quizzes, but definitely on the assignments, I might give some questions on the first and second normal form. It's there also in the PowerPoint slides I put up. So therefore, so the question here is, because there is some redundancy, it might be a good idea to divide the table into Boyce-Codd normal form. So R is in third normal form but not in Boyce Codd normal form. So, so the question is that, how do we, divide this into Boyce Codd normal form? So, so I'm trying to see, should I give the definition of Boyce Codd first? Okay, so let's just say that, before I even give the definition of third or Boyce Codd normal form, let's say like, okay, how should I divide this table R so that I remove the redundancy? So, so one way of dividing this could be, so one way of doing it, I could do it in two particular form, because remember, there are two keys out here. You have D number and school and D number and building. Both of these are keys out here. And then you have building goes to school. So one way of dividing this could be, you could do, so you could do R1 to be, so in this case, you have building. It is a key. I just want to make sure that was the one. Yeah, building goes to school. And then you have R2, which is, okay, so then we have building determines school, and then you have D number and building. That determines D name. So that this is the way you would actually divide it. If you were, I mean, this is, it's not in Boyce Codd normal form, the original R. So you could do it as R1 is to building to school, and R2 is equal to D number, building, and D name. So in this case, you have two different tables, and these two tables are, there are no redundancy or anything in these two tables. So actually, these two tables are in Boyce Codd normal form. But I haven't yet given you the definition of Boyce Codd normal form, but I will give you the definition right now. So the definition here is, if you have a functional dependency where again, A bar, I'm going to keep it as A bar, goes to B bar in R, then A bar must be a key or a super key of R. So that's the definition of Boyce Codd normal form, is that if you divide, so it's actually a simpler definition than third normal form, because what this one is saying is that if you have a functional dependency, A goes to B, then A has to be a key or a super key. So, so in the previous case, FD2 out here, FD2 building was not a key. So that's the reason out here. So that's why R is not in Boyce Codd normal form, it's in third normal form. But now if you look at R1 and R2 out here, you have building determines school, and then you have D number, building determines D name. So because of that, in both these cases, you have the left-hand side is always a key. So therefore, R1 and R2, the way it's set up out here, it is in Boyce Codd normal form. And I also just want to show you, since I put up this example, I just want to show you that by dividing it into R1 and R2, so if you do R1, which is building and school, So you have R1, and then you have R2, which is D number, building, D name. So you have Kingsbury, Morse, Kingsbury, Thompson, and then you have D name, which is CS. Okay, so okay, no, if you look at it, we have brought it down to R1 and R2 out here, and by dividing it into R1 and R2, we have we've removed the redundancy that was there in the previous table, in the table R. So Boyce Codd normal form is far stronger than the third normal form. So do you have did you understand this example and why the table R is in third normal form but not in Boyce Codd normal form? So because sometimes, there is this question, see, what happened instead of dividing it into R1 and R2. So out here, this is the way we divided it. So let's see. This one copy. Okay, so we divided it into R1 building, school, and R2 D number, D name. And like I said, R1, R2 are in Boyce Codd normal form. And R is equal to R1 join R2. Okay, so all of this is really good, but remember this functional dependency that we had earlier? So we had this functional dependency, building goes to school. And then you have we divided it into building and school, and then D number, building, and D name. So this is, this one is fine. But if you now go back and look at this particular functional dependency, if D number, school determines D name and building, by dividing it into R1 and R2, we have kind of lost this dependency, So so when you kept the table the way it was originally, you could see that this dependency was there. The D number and school together determine D name and building. But when you are dividing it like this, you are actually losing this dependency. Because if you just look at these two tables, R1 and R2, you can't, it's not easy to, unless you kind of join them together, which means you're getting back the original table, you don't see this dependency at all. It goes out. So that is one of the problems of Boyce Codd normal form, is that you can lose some dependencies that are there in the original data. So because if you had left the table the way it was originally, this R table with all of the stuff, by just looking at the table, you can find the dependency. Also, if you have a program, so this is a tiny table, but if you have, some program that just looks through the table to find dependencies, it would find that dependency. So, and it's a meaning, there's some meaning there that could be useful. Um, uh, so that part you kind of lose when you bring it down to Boyce Codd normal form. So, so do you understand the point that I'm trying to say? Did everyone kind of get this?
Now, is the relationship still logically enforced? It's just not obvious that it is from looking at the tables?
Yeah, but that's the problem, because once you divide them into R1 and R2, it's not that easy to enforce it. At least directly. We will talk about things like constraints and triggers and all later. So a designer would have to do something like that, and that is a bit complicated. So sometimes, and if you do not put that constraint, so sometimes, putting all these constraints and triggers, and we'll talk about that later in the semester about how we put them. Unless something is extremely important, that if you think that this constraint should be put in, you won't like just, you might just say, you know what, it's not worth putting that overhead into it, so let's not enforce that constraint there once you divide it. So it's very possible that when you divide it into R1 and R2, you just kind of lose that completely. And if it's important enough and you want to enforce it, you'll have to do it. You can't do it directly. So like if the table had been directly put like this, the original R table, you could have enforced it by this, primary key, the key rules. You could say that this is a key and that is a key. So that rule would automatically get enforced. It's not a big deal. It's not a big overhead. But the moment you put it down has two different tables like this, either you lose that constraint altogether, that FD1 constraint, or if you want to enforce it, you will have to write a constraint or a trigger, which we'll talk about later, to enforce it, which is an overhead. So that's one of the problems. That's one of the reasons I said that sometimes as database designers, you might decide that you are not going to bring it down to Boyce Codd normal form. You're going to leave it in third normal form because you want to keep those functional dependencies there. So it is a design choice. So, so if you do keep it in third normal form, there is going to be that redundancy that I mentioned earlier. But you can keep that constraint in. So it's one of a design choice, actually. So from this point onwards, I would say that's why I said right in the beginning that at a very minimum, bring tables down to third normal form. Up to third normal form, it's really good. If you leave things in second normal form and all, there are going to be a bunch of redundancy, which brings all that insert, delete errors and stuff. So at a very minimum, you bring it down to third normal form. But from that point onwards, by the time you get to Boyce Codd, you could be losing functional dependencies. And further down, by the time you go to fourth normal form, you're losing further stuff. And fifth normal form, I would not even recommend you go down to fifth normal form. So therefore, typically tables are left in that, third normal form, Boyce Codd normal form, and sometimes fourth normal form too, because it has multi-value dependencies and it's a good idea sometimes to bring it down to that one. But it's a design choice and you should be aware of it. I hope this part is kind of clear, the third normal form and, the bringing it down to Boyce Codd normal form. Also, just as an aside, I wanted to say that, I have always said that if you divided, I've been saying this from an early, that if you just randomly divide tables, you can lose data. Because I want to do Boyce Codd, but we're just 4 minutes away from the end of class. So I would rather just continue instead of starting up Boyce Codd normal form and how to decompose into Boyce Codd normal form, because there is an algorithm for doing Boyce Codd normal form decomposition too. But I won't start it today. So I'll just kind of finish off with this example. So I've always been saying that if you just randomly divide tables, you could get those join anomalies. So the fact that when you divide tables using this algorithm, you are guaranteed that when you rejoin the tables, you will get back the original table. So you're not going to get loose tuples. You're not going to get extra tuples. You can be guaranteed that when you join it, and you can try this out, you join these two tables and you will see that R1 join R2 will bring back this original data. You're guaranteed. Okay, so because sometimes people say like, what's the big deal? Why do I divide like this? What if I just divided? So just, so what if R, the original table R, let me just bring it down. So what if, I divided R into R1 dash, and here you have building, but now R2 dash. So R1 is similar, but R2 dash, instead of bringing down building, what if I just brought down school? Because after all, the original key out here was, because this is what we're losing, the original key was D number and school. D number and school gives D name and building. So why don't I just bring that down out here? So I do. Because after all, that is the key. Okay, so I'm going to do this. And so now I have D number and school gives D name. And so you could try this out, if you did this, the join of these two tables, if you can try joining it. So let's say we do R. So let's say R double dash is equal to R1 dash join R2 dash, and this will not be equal to the original table R. And so if you try this out, you can check it out. If you join them both together, so you're going to get, these, and you'll get more. There are other rows also. You'll have, earth sciences. But if you look at this table out here, this is not equal to the original table. So the original table did not have one CS, SEPs, and MORS. We do not have that in the original table. So this row is not there in the original table. So this row is incorrect. So that's part of the reason. So the fact that you can get the original tables back, R is very much dependent on following the rule that you have to bring down the key from the first into the second table, because otherwise you won't get the original table. Because sometimes students make the mistake when they're dividing, especially when it comes to this kind of example, that they say, why bring down building? Why not bring down school? And that will create a problem. So do you understand this?